In this video, I want to continue off my last part of talking about the Boltzmann equation and the Saha equation, just to add up on what I didn't talk about in my last class, and on the concept of Saha equation. So to begin with, recall that at the end of my last video, I explained the reason why it's physically impossible to have an infinite amount of energy level for an atom. Well, we took a look at the physical example. So Bohr's model tells us that the radius of the hydrogen atom in level n is equal to the following. So R is equal to a times n squared, where a here is a constant, 0.529, or right. So the radius of the hydrogen atom at level n is directly proportional to the energy level it's at. Well, if there were an infinite amount of energy, it would imply the radius of the atom to be infinitely huge, right? But that's not the case. That cannot be the case, because in that scenario, if the radius of a hydrogen atom were to be infinitely big, it would eventually touch another hydrogen atom's nucleus, right? Because when we talk about atoms, we talk about a huge amount of them, right? Like this infinite amount of energy would be true if there were only one atom in the entire universe and there's no other atoms. But that's not the case in our world, that everything around us are made out of a lot of atoms, right? So that cannot be the case, that one hydrogen atom has the radius of an infinitely big value. So that's impossible, because eventually, as the radius expands, it's going to step into another territory of another hydrogen atom. So that's forbidden. So that's the reason why there isn't, and physically speaking, there isn't an infinite amount of energy levels. So what does this have to do with what we're going to talk about? Well, we can do something very clever here, which is we can show that there exists a maximum energy level for hydrogen, such that if it goes beyond this energy level, it steps into another hydrogen atom's territory. So that's forbidden. So basically, we can use what we have just talked about to derive a formula for the maximum amount of energy level available for a hydrogen atom. So imagine we have a hydrogen atom. So I'm just going to draw it. So this is the proton, so plus, and this is electron. So imagine it's right next to an other hydrogen atoms. This is actually incorrect way to draw it, because it makes it seem like they're bonded. But just imagine these two are distinct and they're very close to each other. So the distance between them is, let's call this 2d, where d is the distance of this, of the radius of this sphere, if you like to call it. So what does d stands for in this case? Well, d stands for radius, then also that is also got to be the maximum amount of the maximum value of the radius that it can be, right? Because if it goes beyond d, if the energy level, radius of the energy level goes beyond d, it steps into another hydrogen atom's territory. So that's not allowed. So d here stands for the maximum value that the radius can take before it steps into another atom's territory. So we could write something like d is bigger than or equal to Rn, where Rn is the maximum allowing radius of the energy level. And if we were to approximate the number density, it will be equal to n equals to 1 over 2d cubed, where 2d cubed is the volume of a cube. Well, the reason we use a cube here is because, well, it's a very rough approximation. So imagine this is the volume it takes for the hydrogen atom, right? And the side would simply be the radius. So imagine we have a it's kind of hard to draw this. I'm not sure how to draw this, but you get the idea. We're approximating the volume of this hydrogen to be a cube, and then the side of this cube obviously is d, right? So the volume is 2d cubed, and then the number density tells us for every one atom, it takes up 2d cube amount of volume. So this is what this term here tells us. So we have this term, and we also have, well, radius max. So this is the maximum allowed radius is equal to A0 times n max, right? Because there's a maximum allowed of there's a number of maximum allowed energy level, because it go beyond that energy level, it steps into another hydrogen atom's territory, right? This is going to be equal to D, because like we just done, we literally just defined D, and this is going to be equals to well, what do we have here, right? We have the so A0 times n squared max is equal to D. And if we were to derive for D in this case, it will be 2D cubed is equal to 1 over n, right? You want to get rid of the power, so this will be 2D is equal to 1 and 1 to the power of 1 over 3, because 1 to the power of 1 over 3 is 1. And then you have D is equal to 1 over 2 times n to the power of 1 over 3. So this is our D. So if this is our D, then we have A0 times n squared max is equal to 1 over 2 times n to the power of 1 over 3. So this is what we have here. Then now you can move the A to the bottom. So this gives us n squared max is equal to 1 over 2 times A0 and 1 over 3. And so we basically just take the square root. So this gives us the maximum energy level allowed for the hydrogen atom, for it to not step out for its energy level to not step out its territory and enter another. So this is the maximum allowed energy level for hydrogen in this case. This is like a very rough approximation. Yeah, so this is equal to square root of 2 times A0 times n 1 over 1 n to the power of 1 over 6, right? Because you take the square root of this and you get n to the power of 1 over 6. So this is our max formula. So that's the first point I want to talk about. Well, the second thing is I want to show you guys an example of the Boltzmann equation, right? Remember we talked about the Boltzmann equation. So here's two of them. Remember in my last class I talked about what they're for. So this one at the top is used for comparing individual levels. So if you were to compare the ratio between n equals to 1 and n equals to 3, you would use this formula. And this is more like if you were to compare n equals to 3 to the entire summation of all the possible energy levels, right? So the upper one is comparing one to another one. The bottom one is comparing one to the entire thing. So that's what they're for. So one example question we can go through right here is that we're asked to find the temperature at which number density of hydrogen atoms in the fundamental state is equal to that of its second excited state, right? So what are we trying to find here? Well, what are something that are given? Well, first of all, this is about a ratio between two specific levels. So we will use the this version of the upper version of the Boltzmann equation. So this is going to be equal to Gj. And I also want to talk about this G value real quick. Not going to get too deep into it because it's not really related, but so this is going to be equal to, yeah, this is it. So in this case, what do we know? What are the information that we know? Well, we know that the number density of, well, we're trying to find the temperature. The temperature is the thing that we're trying to find. And it already tells us the number density of hydrogen atoms in the fundamental state. So at n equals to 1, it's going to be equal to that of its excited state, right? So when two things have equal value, what's their ratio? Well, their ratio is 1, right? So what we're going to have left is just going to be 1, because you have the same number on top, same number on bottom. That's the condition given in this question that says fundamental state. So ground state is equal to that of its second excited state, n equals to 3. So actually, let's write it in terms of the numbers. This is more clear. So m1 over n3, g1 over g3, e to the power of negative, the energy difference is E1 minus E3, KT, right? And then, as I said, this is going to be 1. And for this degeneracy value, I want to talk about, well, what is the degeneracy? Degeneracy tells us like the way an electron can take the different sort of way an electron can take place, and or can take, it tells us the specific configuration that the particle can have while still having the energy. So given each energy level, so at each energy level, so you have n equals to 1, n equals to 2, n equals to 3, there are only a certain numbers of way or configuration that particle can have. So this configuration, or this number of how many ways the particles can take in these configuration, is what we call the degeneracy. And I'm not going to get too deep in that because they involve some concepts such as spin or momentum stuff that we're not going to get too deep into. But basically, you need to understand that in most of our example, we're going to talk about hydrogen, because all of these degeneracy and stuff gets way more complicated when it's involved other elements, because, well, hydrogen is very simple. There's only one proton and one electron. So 1. And then the degeneracy formula for hydrogen. So G hydrogen, I'm just going to write this. You need to remember this is equal to 2n squared. This is the general formula for the degeneracy of hydrogen at different energy level. And G1 is going to be what? 2 times 1 squared, so that's going to be 2. So let's write what we have here. So G1 is going to be 2. G3 is going to be 2 times 3 squared is going to be 18. And then E1 is going to be 0 eV because we're at the ground state, right? And then E3, what is this going to be? Well, recall the formula for energy level of a hydrogen atom at different energy level is En equals to 13.61 minus 1 over n squared. So if you were to plug in E3, this would be 13.61 minus 1, 3 squared. So if I were to plug this into the calculator, this would give 12.09 eV. So we have all the variables here. So if you were to plug all of this in, so we have the ratio as 1 on the left, right? And then 2 over 18 e to the power of negative 0 minus 12.09 eV, right? Over kT, right? So this is what we have. And then this becomes, if you do some algebraic manipulation, this becomes 12.09 eV over kT is equal to ln to the 9, right? The ln is here because you got rid of the exponential. And then we know the constant K is 8.617 times 10 to the negative 5 eV K. If you plug that into the equation, now you know everything, right? You know EV on the top, you know K, and you know ln 9. So you just have to manipulate for T, and then the T you get obtained at the final is about 63,900 Kelvin. So this is the temperature you would get in order for the number density of hydrogen atoms to be in the fundamental state to equal that of its second excited state, which is n equal to 3. So what this question is essentially calculating is using the Boltzmann equation to calculate the temperature needed for the number of fundamental state to be of the same of the n equals to 3 states. So now we're done talking about this. So before we do the next example question, I want to first talk about the idea of Saha equation and what Saha equation tells us. So the Saha equation goes something like this. Saha equation goes Ni plus 1. Ni is equal to 1 Ne. I'm going to explain these terms one by one. Just let me write it down so you guys can see what this equation is all about. So take a look at this equation and see, look at this KT at the bottom. Look at the variables in here and what they mean. Well, this is the Saha equation. So it tells us the ratio between different ionization states. So you recall in this example, so what these are for is telling the difference between two energy states, right? Like the above is between energy n equals to 1 or n equals to 3, like what's the ratio between them? So these two are associated with the energy level, or the ratio of the energy level. But what this is for the ratio of ionized hydrogen versus neutral hydrogen, for example, or singly ionized carbon versus secondly ionized carbon, or something like that. Like this equation is for the ratio between ionized elements. So instead of energy level, so this is for ionization. So you could ask, like, what's the ratio between this is a neutral hydrogen, right? What's the ratio between this neutral hydrogen and an ionized hydrogen? An ionized hydrogen basically is a proton, right? Because it's only got one electron to lose, and when we lose the electron, there's only one proton left. So that's what the Saha equation for, is calculating the ratio between different ionization states, whereas the Boltzmann equation is calculating the ratio between different energy levels within the same ionization state, right? So some of the variables we have here, I just want to quickly go through them. So Ni and Ni plus 1 are the population of neighboring ion of a given element. So in this case, if, for example, neutral hydrogen, the population of neutral hydrogen versus the population of ionized hydrogen. And Ne here is I'm going to write this down. Ne here is the number density of free electron, which I'm going to talk about in a second, in gas. So this is the number density of free electron, and T is the energy here, and Me stands for the mass of the electron, and pi, K, H, all these are just constants, right? And Ui here stands for and Ui plus 1 stands for the partition function. And E iron is the ionizing energy of the iron I from its fundamental energy level. So for hydrogen, this will be 13.6, as we talked about. Right, so this might seem confusing. Like, you might wonder, what is this even about? Well, let's look at the example question. Well, the example question asks, for a given star, calculate the fraction of a neutral atom in a gas composed of pure hydrogen at a depth where the temperature is 12,000 Kelvin and number density is 2.0 times 10 to the power of 15 centimeter to the power of -3. So what are we given? Well, we're given T is equal to 12,000 Kelvin, and the number density is equal to 2.0 times 10 to the power of 15. Let me do that. Right? How do we solve this? Well, let's first write down the Saha equation. Right, let's just copy it over here. So I'm just gonna quickly grab this, bring it up. Right, so this is our Saha equation. Well, let's first write it, right? So we want to find the fraction of neutral atom in the gas composed of versus pure hydrogen. So that would be HII versus HI, right? This is ionized hydrogen. This is neutral hydrogen, where none of the electron has been stripped away. So let's write our Saha equation of these two. Well, you'll have N2, let's call it 2, over N1. This is going to be equal to 1 over NE, the entire thing here, right? And then 2 times our partition function for the ionized hydrogen over Ui, and then e to the power of negative E iron and KT. And like we talk about, what do we also know? Well, we first know the temperature. We write down this, and then we know the number density. 15 centimeter to the power of negative 3. We know that E iron is going to be equal to 13.6, right? E. And here the the partition function for the partition function for the ionized hydrogen is gonna be equal to 1. Why is that way? Because when you have a hydrogen, this is a neutral hydrogen, and this is a hydrogen that has been stripped of its electron. It's just a proton. And when it's just a proton like that, you can assume that it has one energy state, right? So it only has one energy state. Well, remember the partition function is the summation of all possible energy states. So in this case, where it only has one proton, there's only one possible energy state. So that's why Ui is equal to 1. And you might ask, well, what is Ui? Well, in our question, we're given that we were to assume the partition function of neutral hydrogen Ui to be 2. So Ui is equal to 2. So now we have all the values. So what do we do now? Well, if we substitute everything into the equation, we can eventually manipulate it into the following form. So that I'll leave that as an exercise for you guys to do. But if you just plug in all the constant here, right? You have 2 pi, mass of the electron, KT, H, Planck constant, Boltzmann constant. These are all constants we have talked about. Like if you just plug in all, it's just gonna be a big ugly number, which is what we're gonna have here. This is gonna be equal to 6.156 times 10 to the power of 15 centimeter, right? And this is gonna be 6.498 times 10 to the power of 14 centimeter, negative 3. So this is actually gonna give us the value for Ni, so the number of neutral hydrogen. So if we want to find the fraction between, so if we want to find the fraction of neutral hydrogen, we can use the following formula, which is the fraction formula. It tells us that you have N, so the amount of, so N1 over N1 plus 2. So what does this tell us? This tells us how much N1 is in each N1 plus N2, because that's the entire gas, right? So what fraction of N1 is equals to the total of these two? And then if you were to plug in the values, then this will just give us 0.245 or 24.5%. Yeah, that seems to be about right. And then you might ask, how do you solve for N2? Well, if you look at the equation here, you have N1. If you've already found N1, you're going to substitute that in to find N2, which you can just calculate that and then do this part as the calculation. And then you can get that the neutral part of the part of neutral atoms at this temperature is going to be 24.5% out of all the hydrogen gas that is here. So that's what this is gonna give you. So today's key takeaway is talking about the Saha equation versus our Boltzmann equation. Because remember, I'm gonna say this again for what they're for. The Saha equation is the ratio between ionization state. And Boltzmann equation is the ratio between different energy level within the same ionization state. So when we talk about the Boltzmann equation, we're talking about the same ionization state but different energy level. Whereas in the Saha equation, it gives us the ratio between different ionization states. So you can, for example, use this to calculate CII versus CIII, right? So this will be singly ionized carbon. This will be secondly ionized carbon, right? So you could use it to calculate the ratio between ionization state versus Boltzmann equation is the ratio between different energy levels. So that's all I gotta talk about for these two equations, and I'll see you in the next class.